Starting at the surface, we can see that atmospheric circulation is directly tied to ocean circulation in distributing the world's energy budget. When the wind blows, the water moves, essentially. So we can see in this image a plot of the major wind-driven currents around the world. These currents are forced or pushed directly by the atmosphere. So starting here in the North Atlantic, we have the trade winds blowing to the west. These are the easterlies, the southeast trade winds. They're going to push the water along with them towards the west. When we reach the western boundary of this ocean circulation pattern that we'll call a gyre, we see the direction of the water circulation changing. It switches from westerly to northerly, and then ultimately it's going to be entrained by the westerlies, which are blowing to the east at these mid-latitudes. These westerlies are going to push this ocean gyre to the east, and once it reaches the European continent and West Africa, it's going to be deflected to the south, and it's going to continue with this pattern that's forced by the atmospheric circulation. Easterly trade winds here, mid-latitude westerlies up here. Same thing goes in the Pacific, and in the southern hemisphere, the opposite scenario takes place because the winds are blowing in the opposite directions at specific latitudes in the southern hemisphere. And these are known as the major wind-driven currents. Circulation in the ocean is different than that of the atmosphere in a couple different ways, very important ways though. Again, we see a map here of the globe, in this case with some of these gyres named. These gyres may have spin-offs that become subsidiary currents. In this case, the North Atlantic gyre has a Gulf Stream component that most of us are familiar with. This Gulf Stream is going to work its way from the warm tropical waters, semi-tropical waters of the Caribbean, to the high latitudes off of maritime Canada. It's deflected to the east, and then it bifurcates. It splits into the Norwegian current, or the North Atlantic drift as it's known, and it becomes the Canary current flowing to the south. Now we have another current up here, the Erminger current, which is warm water that splits going to the east and to the west of Iceland, which is this island here. And that's colliding with this cold, deeper water East Greenland current that's moving to the south, ultimately joining up with the cold, deeper Labrador current that moves past Labrador here. This is what generates what's known as Iceberg Alley. Icebergs coming off of Greenland and to a lesser degree up here in Canada, getting entrained in these currents and forced south. So if you visit Newfoundland, you can often see icebergs cruising by the coast. That's just kind of neat. What's driving this difference in circulation? The primary thing that's driving this difference is that the atmosphere is heated from below and the ocean is heated from above, with 90% of insolation absorbed in the upper 100 meters. That's not a typo. The atmosphere is heated from below. The ocean is heated from above. This energy is going to be stored somehow, and we're going to see where it's stored in a moment. So what does this mean, heated from below? Well, the atmosphere is basically transparent to incoming insolation that has relatively short wavelengths, relatively high frequency insolation, travels through this transparent atmosphere, strikes the Earth's surface, is absorbed with 100% efficiency because the Earth is a black body, and then it's re-emitted at a longer wavelength. In this case, because of the Earth's average temperature, that wavelength is going to max out in the infrared range. The Earth's surface is heating the atmosphere from below. The ocean is receiving insolation from above. That insolation is traveling as far as it can into the ocean, but most of it's going to be absorbed in the upper 100 meters. And anyone that's gone snorkeling or scuba diving can tell you that when you look down in a column of water, it gets dark. If you dive down 50, 100 feet, say 30 meters, most of the light goes away. You're going to want to bring an auxiliary light with you, a flashlight of some type. Once this water is warmed, again, most of the heat is going to be absorbed in the upper portion of the water, the upper 100 meters. This means the ocean heat content, the storage of this energy, is going to be concentrated in the upper layers of water. In this case, it's divided between 0 to 700, 700 to 2,000 meters depth. So 0 to a little over a half a kilometer depth, and half a kilometer to 2 kilometers depth are the two categories here. Most of the heat that's retained by the Earth from the sun is retained in the upper 700 meters of the ocean. A significant proportion of that heat is going to be stored in deeper water, from 700 to 2,000 meters depth and below. And then what we're familiar with, the land, ice at the poles, near the poles, Greenland and Antarctica, the ice caps on Iceland, again, the surface features, and the atmosphere just above the Earth's surface, is going to store some heat, but comparatively little. Most of this heat is produced in the infrared range, and it's emitted into the atmosphere to heat the atmosphere. The atmosphere then circulates that energy, and it's ultimately going to be removed from the Earth system at about the same rate it's received. Another thing to consider in terms of circulation of the ocean is the influence of temperature on the water density. We'll start out with a simple scenario here, freshwater. In freshwater lakes, such as the lakes here in Canada, we see a division during the summer of 3 different levels. We have the epilimnion here, we have the metalimnion here, and the hypolimnion here. These different layers of water are going to circulate somewhat independent of each other. At the surface, you dive into a lake in northern Saskatchewan in the summer, late summer usually, that water is going to feel relatively warm right here at the surface. If you hold your breath and swim down 3-4 meters, it'll be dramatically colder. And if you were to continue on down to the bottom of the lake, then you probably wouldn't need to go very far. You would hit water that's about 4 degrees centigrade. So maybe 20, 24 degrees at the surface and about 4 in the deeper water. So the net result is, during a season, we'll say we start in the wintertime when the lake is ice covered, we see the temperature decreasing to about 0 right at the surface, right beneath the ice, increasing to about 4 degrees quickly below the ice, and then maintaining a steady temperature all the way to the bottom of the lake of about 4 degrees. That's the temperature of maximum density of fresh water, normal Earth surface pressures. During the fall and spring turnover, when the lake mixes from the top to the bottom, the temperature has to be isothermic, about the same from the top to the bottom. Usually this takes place when the water reaches a temperature of around 10 to 12 degrees or so. In the summertime, the lake is stabilized because warmer water is less dense than colder water, and this surface water will continue to get warmer and warmer as long as the air stays warm, as long as the lake is receiving significant insolation and the mixing isn't too great. Because of this warming, though, the mixing tends to be limited to near the surface. Eventually, we're going to reach a place in the lake, depth-wise, where the temperature changes. There's an incline in the temperature versus depth. So we'll call that a thermocline. So the thermocline is a tilt in the thermal record with depth. So no thermocline, it would be isothermic, same temperature all the way to the bottom. With the thermocline, we have 25 degrees at the surface, temperature decreasing substantially within the thermocline until we reach the hypolimnion, where the temperature is probably going to reach a low of about 4 degrees again. So this is a simple scenario. This is what we see in freshwater. The ocean is different, though. There's something about the ocean that changes this thing, throws it on its head, and that's salt. The presence of salt, of dissolved solids, of ions, increases the density of water. Seawater is denser than freshwater. Because warmer surface water is less dense than cooler water, this increases stability if the water is fresh. If the water is not fresh, as most of the water in the world, then the surface heating is also going to increase evaporation. When water evaporates, the water molecules go away. The dissolved solids stay behind. The net result is the water becomes more salty, more saline, and therefore more dense. The thermal inertia of the ocean prevents it from responding directly to changing insulation on a small scale, the way that air is affected. So here we have a playa, an extreme evaporative environment. And you can see that the evaporation has proceeded to a point where salt crystals are forming in the water or adjacent to these pools of water. If left alone, this would all turn into a solid beach of salt at some point. Well, it looks like fairly soon. This could be Death Valley. I'm not actually sure. It sure looks like Death Valley. You have a big alluvial fan here of weathered feldspars coming out of these granitic rocks. At least that's what it looks like to me. And in dissolving these feldspars, you free up a lot of ions. These ions make their way into the lake here. This lake evaporates, and those ions precipitate as salts. So they start out as feldspars, they end up as halides, or salt crystals here.